A confirmation regarding the audio, please, guys. If you're able to hear me out perfectly well, kindly confirm the same. Thank you. We shall be starting in a couple of minutes. Okay. So, hello, a very warm good evening to all of you, and welcome to Byju's Exam Prep. Welcome to another session of Geomorphology, where today we shall be further looking into the aspects of earthquakes, volcanoes, and landforms. So, basically, yesterday we had finished the portion of continental drift, or rather the plate tectonic theory, where we discussed the various different types of convergences, divergences, transform plate movements, and we also looked at certain different types of plate movements which lead to different landforms and geophysical characteristics which are resulted. Then we started looking at the aspects of earthquakes. In the case of the earthquakes, we have till now looked at the portion with regards to what is earthquakes. We have tried to look into the aspect of, for example, when the earthquakes do occur, then after that, the energy is released in the form of seismic waves. So those seismic waves, they are classified in the form of P waves, S waves, as well as the surface waves. Now, the body waves, that is the P and S waves, they travel through the interior of the surface of the earth, and they travel up till the surface. And thereafter, on the surface, ripples or disturbances are created, and that is where you have the creation of surface waves. Most of the destruction that we see around us are carried out, in fact, by the presence of these surface waves. Now, then we also looked at that when you have these earthquakes which occur, these earthquakes, basically when they occur underwater, in the case of oceanic bottoms, that is when the base of the oceans, they are disturbed, and that base of the ocean disturbance, that leads to generation of very large waves, and these large waves, they lead to causation of tsunamis, and those tsunamis, they have a significantly damaging impact on lives and livelihoods. Now, today, we shall be starting the discussion from the portion of geographical distribution of earthquakes and what are the earthquake prone zones across the globe. There, we will take a look at the relationship between the plate margins and where is it that we experience greater occurrence of earthquakes. We will also be taking a look at how these are also the areas where you will observe certain volcanic eruptions and activities to also occur. Then, after that, we shall be taking a look at the earthquake prone areas in India and moving ahead into volcanism and landforms. Okay, now, before we initiate the discussion, a couple of announcements to make. First of all, for geography, because of the last Friday's class, which was cancelled, we'll have an extra session on Saturday from 7 a.m. to 11 a.m. So that is when we will be having an extra session for geography. It is not necessary that we will carry it out till 11. The moment where we feel that we are or there is enough amount of information flowing through our heads, we'll take a call accordingly. So on Saturday, that is 7 to 11, we will have this extra session, and then another one, that is from today onwards, the recorded sessions of the BHLP lectures, that is something which shall be available on the app for your perusal and for your revision purposes as well. Okay, so you will have the recorded lectures of the live sessions available on the BP app now. Okay, now then we come to the portion of geographical distribution of earthquakes. Okay, right. Yes, many of you had been demanding about the recorded versions, so that will be available to you. So, and please use that for revision purposes. Please don't try to use it for the first hand information purposes. Okay, it will be available on BP app. That is where it will be available. Now, then we come to the portion of global distribution of earthquakes. So this is in simple terms, across the globe, where do we experience the occurrence of earthquakes in general? Now, this is something which is relevant for your mains examination. Okay, for the mains examination, this is a portion which is going to be important, and frequently UPSC has been asking questions from this portion with regards to discuss where is it across the world that you experience frequent occurrence of earthquakes, or why is it that the earthquakes occur. Discuss upon them by elaborating upon the regional distribution of earthquakes. So such kinds of questions are always asked frequently in the optional area as well as in the portion of general studies. So you can always expect a direct question coming from there. Now, when such a question is asked in the examination, ideally, you should be able to draw a kind of a rough map and indicate the areas where the earthquakes do occur. Now, first of all, we have to understand why is it that the earthquakes occur. So, by the aspect of the plate tectonics that we have studied till now and the other portions that we are aware of, we have basically looked at the fact that whenever the rocks, they will have a movement with respect to each other, that movement will never be smooth enough. That movement will always lead to displacement in the land surface. That movement will always lead to, either if it is due to subduction, divergence, or transform movement, that will lead to a rough movement, a kind of a staggered movement. And whenever the rocky surfaces, they overcome their force of resistance, they will release huge amount of energy that we experience in the form of earthquakes. So broadly, earthquakes, they will occur where? Generally across the plate margins, plate margins, as well as along fault lines across the surface. Fault lines, basically wherever you have the presence of cracks, right? Large cracks which develop. Any kind of readjustment of the rocks thereby, that can lead to the occurrence of earthquakes. Okay. Now, if you take a look at where is it across the globe that you experience these aspects, plate margins refers to the boundaries of the plates. Okay, this refers to boundaries. Okay, so that is where it is something which is mostly experienced. Now, if you basically look at where across the entirety of the planet do these conditions do they satisfy or are they fulfilled, you'll find that there are two such broader regions. One is the circum-Pacific earthquake belt or the Pacific ring of fire that we have studied. Why? Because all around the region of Pacific, you have regions where either you have transform plate movements, for example in some area around Yuan the Fuca plate, or rather in the region of some portion of Pacific and North American plate. Otherwise, you have either convergence in terms of oceanic convergence or oceanic continental convergence. So whenever you have that kind of a situation, it will always lead to occurrence of earthquakes. So in this region, you generally have convergences. And what kind of convergences do you experience here? We have oceanic, and oceanic continental. Okay. Now, That is something which you will experience in these areas. That is why in these areas you do experience the occurrence of lot of earthquakes. And the other region is the Mediterranean Asia earthquake belt. Now in the region all the way spreading from the region of to the north of Mediterranean Sea all the way to the region of Himalayas, there also you have convergences which happen. And convergences what kind? In the region of Mediterranean, you have the oceanic crust and the continental crust converging, whereas in the region of Himalayas, we have a continental convergence. So there also you have the occurrence of earthquakes. So if you were to dot or map out the earthquake prone zones across the world based upon the plates that are present, you will observe that broadly all of these they are available, or all of these they are experienced across the plate margins. Almost all the earthquakes that you will observe, they are experienced across plate margins. Observe the region around the Pacific plate first of all. Around the region of the Pacific plate, even in the region of the boundary between the Pacific and the Nazca plate, that is the East Pacific rise, there also you experience earthquakes. But nonetheless, look at it, where is it that the frequency is the highest? Frequency is highest where there is a distinct convergence which is happening, right? For example, South American plate and Nazca plate, you have the Nazca plate which is going underneath the South American plate. That is where here you have the Peru-Chile trench which is present. It is across those areas where there is a kind of a convergence which takes place and the region starts subducting. So that is where you have very frequent causation of earthquakes. Then after that, even in the region around the Caribbean plate, here also you have a combination of transform movement and convergence. That is why in the region around the Caribbean islands, including areas around Haiti, uh, areas around Mexico, they experience very heavy earthquakes because of the plate movement. All around the Pacific, if you will observe, then look at it in the region around Mediterranean, spreading across Iran, Afghanistan, Pakistan, and also the Indian subcontinent. That is again where you do experience earthquakes. Now, in all these areas, you will observe, why is it, what kind of plate movement will lead to occurrence of earthquakes here? Here you have divergence of plate movement. North American plate is moving away from Eurasian plate, and South American plate is moving away from African plate. So that is why in the divergent plates also, as the plates they move apart, as the molten materials they try to come to the surface, that also creates a kind of a disturbance. Okay, now here this is the region around Turkey and Syria, which frequently and recently also has experienced earthquakes. This is the region around the East African Rift Valley, where the land is splitting into two. That is also going to experience earthquakes. So these are earthquake zones. Okay. Now, then after that, what we will do is we'll juxtapose this image, or we'll look at this image along with a reference pointers with regards to global distribution of volcanoes. Okay, that is something which will clear a lot of ideas and it will clear a lot of concepts, because we know that whenever you have convergence of plates or divergence of plates, that can also lead to volcanoes to erupt. So look at these areas where the earthquakes occur, and you will find a resembling similarity with regards to the areas where you will experience the volcanoes to erupt. So here, these are the regions of frequent volcanic eruption. Again, you will observe the region around the Pacific plate. Okay, the entire region around the Pacific plate, including the region around Philippines, Japan, the region around the Bering Sea. Then furthermore, in the area around South America, western part of South America, then Barren Islands or the Andaman Nicobar region, then across the East African Rift Valley, then across the divergent regions of the Atlantic plate. So obviously, this is the plate margin where you have the occurrence of both earthquakes and volcanoes. Now, what about India? When we talk about India, then what is the condition in that? So basically, here you will observe in this map, look at the region around the Indian plate, you will observe a great frequency of earthquakes occurring in the entire region, spreading all the way up till the area of Gujarat. And yesterday, while discussing, we had discussed about the fact that around the region of Gujarat, because you have a meeting point of three different plates, that is, what three different plates? You have the presence of the Indian plate, Arabian plate, and Eurasian plate. So, any kind of movement of any of these plates will always lead to earthquakes occurring in Gujarat. So, that is why Gujarat is one of the areas which is very prone to earthquakes. Then, other than that, if you look at the earthquake zonation for the rest of the country, you will observe that it is the Himalayan region which is prone to earthquakes. And high intensity, high magnitude earthquakes have been experienced in the Himalayan region. So, this map gives you an idea with regards to the classification of the hazard zonation, that which area experiences or what is the probability of earthquakes happening in this region. Now, in the region of Himalayas, because you have convergence, continental convergence, continental convergence. That is why there is a significant amount of deformation which is experienced, and that is why this is a region which experiences frequent earthquakes occurring, be it the Kulu earthquake or the Kangra earthquake, be it the earthquakes which keep on occurring in the region of Uttarkashi, Chamoli region, in the entire area of Uttarakhand, be it the region of Nepal, be it the condition of the very strong Bihar earthquake 1934, be it the Kathmandu earthquake of 2015, be it the Assam earthquake. These areas, they are frequently the ones which frequently experience high magnitude, high intensity earthquakes. That is why in these areas it is said never to carry out any kind of a construction work which in a way changes the pressure induced on the rocks or in any way exerts additional pressure on the rocks. Okay, so that is why it is always advised that please don't build large dams in these areas. Why? Because what tends to happen, we have to take a look at the rocks as a solid, right? Imagine that this is a solid, you construct a very large dam over this area. So when that dam is something that you construct, and all that millions and trillions of gallons of water that are held by the dam, it will exert significant huge amount of pressure on the rocks. And due to this, what happens that if the rocks are already unstable, as is the case in the entire Himalayan zone, there the rocks are already experiencing huge amount of stress. Now, on top of that, if more stress is exerted, that can very easily lead to development of cracks, right? Because you exert stress, the rocks will be able to withstand to some extent. You exert more stress, maybe they will be able to withstand slightly more. But if you keep on continuing, eventually cracks develop. And when these cracks develop, let's say a crack develops here, let's say a crack develops here, then what will happen? Then this rock can simply slide past the other, and that will lead to not only the breakage of dam but huge earthquake or earthquake of very high magnitude. That is why in the Himalayan region always it is advised never to construct very large dams. That can be disastrous. But China is doing so, because very well China can do anything that it wants, and China is building large dams in the region just to the south of Tibet. In this area, across river Brahmaputra, China is constructing 5 large dams. And for the policy planners and the policy makers of China, it is a kind of a zero risk game for them, because as they end up behaving, Here in this area, you don't find a greater amount of population, Chinese nationals settled here. This region is sparsely populated. So if you apply a kind of a brute logic, you'll find that even if the earthquakes occur here, the Chinese nationals and the Chinese mainland will not be impacted significantly, whereas the regions of Nepal and Bhutan, they stand to suffer hugely. So that is why China can do what China can do. We cannot do what China can do, and that is probably for the good as well. So, other than this, Gujarat is one of the areas which is frequented by earthquakes. Other than this, some portion in Maharashtra, there also, because of a development of a crack or a fault line, there also you have occurrence or causation of earthquake. Okay, so here in India, it is classified from zone 2 to zone 5. Why zone 2? Why not zone 1? So this was a kind of a behavioral classification, if you will observe, because when you have classified something as zone 1, thereby it in a way gives an idea that that region might not ever experience earthquake. There is absolutely limited probability of an earthquake occurring there. But that is not the case. So that is why, and time again, earthquakes have surprised us regarding where they have occurred. And generally, what happens is if an earthquake occurs in a place, the scientists go there, they study, and then many of the times after that, they are aware that, okay, there is a fault line here as well. For example, take the case of Latur earthquake. Where is Latur situated? Latur earthquake in Maharashtra. Now, that is something which was not expected, because in the region of Maharashtra, you will basically end up finding a kind of a homogeneous rock formation and homogeneous rock surface without the existence of any plate boundary. In the region of Gujarat, fair enough, there is a plate boundary. In the region of the Himalayas, fair enough, there is a plate boundary. But what about the region of Maharashtra? There is no plate boundary. So there was no one who was expecting the occurrence of earthquake there. But an earthquake did strike. In the year around 1992, Latur was struck by an earthquake, even though the magnitude was only close to around 5.2, but still Latur experienced a lot of destruction and devastation. So later on, when the inquiry was held, it was observed that there is a fault line which had developed around Latur, because as the Indian plate was moving, there are certain areas due to resistance, they develop cracks. So that is why you never know where these fault lines can develop and how quickly can they develop. So that is why it is classified from zone 2 to zone 5. Okay. Now, today also, by the way, an earthquake has occurred. A massive earthquake has occurred today as well. Can anybody let me know where it has occurred? Very good. At least you are the ones who are following the current affairs. Today, not Turkey and Syria, there it is not today. Yes, it has occurred in New Zealand. And again, if I take you back to the map, observe how frequently in this entire area, how frequently there is occurrence of an earthquake. And that is where here you have the Tonga Trench as well, Tonga volcanic eruption as well. Observe, this is the entire area where you will find volcanic eruptions to occur as well, because there's a plate margin. So this is where a high magnitude earthquake, close to around 7.1 magnitude earthquake, has occurred today. So be on the lookout for this. Okay. Now be on the lookout for this, not because I want you to maintain a kind of a chart that where earthquake has occurred, because on a daily basis you have occurrence of 1,000 earthquakes plus on a even if you consider the ones which have a greater magnitude. On a daily basis, more than 1,000 earthquakes, they shake the earth's surface. Many of us do not even end up feeling many of these. But then Why I want you to take a note of where earthquake has occurred, because if you will then try to analyze why it has occurred there, you will come across these news stories in the current affairs. But what I want you to do is that from now onwards, try to analyze that why it has occurred in that place. Invariably you will come across a solution that there is a plate boundary, an active plate margin in that region. That is why it has been occurring there. So observe it on your own from now on, and this portion will be much more clearer in aspect. Okay, right. Now then we come across induced seismicity or induced earthquakes. So, what do we mean by induced seismicity or induced earthquakes? So, these are the kinds of earthquakes which do not occur naturally, but because of human actions. That is where we are able to lead to the shaking of the earth's surface, causing these earthquakes. Okay, so that is why referred to as anthropogenic anthropogenically induced earthquakes in many of the cases, right? Because it is caused by us humans. We humans are able to cause a lot of devastation and destruction all around us, right? Be it in the case of forest fires, be it in the case of pollution, we manage it all. So that is how we have managed to shake the earth's surface as well, because of our own deeds. So we have not even left that. So in certain human activities, you will observe the occurrence of these earthquakes. For example, here you have the hydrocarbon extraction. So, which hydrocarbon extraction are we talking about? Here we are talking about extraction of crude oil and natural gas. Okay, we need to remember which are the plates are diverging. Just try to remember the plates, guys. Okay, try to get an idea about the major plates, or slowly and steadily, even if you don't put an effort into it, but if you keep on reading the current affairs, these plates, they do get mentioned in newspapers on a very regular basis. So that is where you will get an idea invariably that okay, this plate here, there is an earthquake which has occurred, there is a volcanic eruption which has occurred. Now obviously when you remember a kind of a plate, you will get an idea about their motion as well. So it is a kind of an information that you don't need to rote learn, but it is something that you can follow with procedure. Okay, now here, how is it that crude oil and natural gas extraction leads to occurrence of earthquake? That is because of the fact that oftentimes the crude oil and natural gas at the time of extraction, it is released with huge amount of pressure, and that huge amount of pressure many of the times blows off the top rock surface as well. It is very destructive, the amount of pressure that is with which crude oil and natural gas oftentimes escapes from underneath. So in that pressure, it can lead to the shaking of the earth's surface or the ground surface. Generally, if you will observe that, yes, nuclear weapons in that localized region will always lead to causation of earthquake in that localized region. All these basically lead to an earthquake in a very localized area. So for example, here, when we say hydrocarbons, or when we say crude oil and natural gas, how is it found? Generally you will find that all this crude oil, that is trapped in between the rocks, and it is basically something which is present in between the regions of the rocks and is able to penetrate the rocks as well. So you have certain areas which are oversaturated with gas and oil. So here, let's suppose, if you consider this to be the rock bed where the oil is present, you will have large rocks. Okay, so these porous rocks, let us say that they consist of oil. Now, there is oil here as well, there is oil here as well, there is oil in between all of them. Now, how do you extract this oil? How is it that you extract this oil? It is present at a depth. Do you simply put down a bucket and start taking it out? No. So, what is done in most of the cases is that you have a pipe which is installed. Two pipes are installed rather. And from one of them, at a very high pressure, and at a very high pressure, you have the application of water jet and air as well. So high pressurized air and water is pumped in, right? And when that pressure starts getting exerted here, automatically, and this is the exit pipe, this is what provides a kind of an exit passage. So when there is a lot of pressure which is exerted, all the materials, they will try to escape that pressure, and that is where they rise up and they simply break through and they are then tapped, right? If so, in the initial days when the exploration has happened and when you have the initial portion of extraction, this is done. Eventually, after 2 to 3 days, or sometimes it might even take 2 to 3 weeks, after that it stabilizes this output in a way the flow is controlled, and then you start storing it and you start extracting it on a regular basis. But in the initial days, when you are extracting oil from a new region or a new oil field, at that point of time, such a huge pressure is exerted by the outgoing gas and crude oil that it shakes the earth's surface in the localized area or in the local vicinity. That leads to earthquakes. Okay. Now, many places. You can take the case of Assam. Assam, in the region around Digboy oil field, they have experienced localized earthquakes because of this. Okay. Now, then we have dams. Now, dams basically are what? These are water storage structures. So when we talk about dams, these dams, they have large concrete sections and large concrete holdings, and they are able to store millions and billions of gallons of water together. So as a result of that, whenever you observe the formation of a dam, formation of a dam, or the construction of a dam rather, this is the reservoir which is constructed. I can see that most of you are still not able to contain the excitement with regards to availability of recorded lectures. I understand it is a very good news for you guys. I understand it calls for huge amount of celebration at your end. I don't know what you will do now. And so please get over it. Concentrate here. Okay, recorded lectures will be available to you regardless of how you ask it, that will the morning sessions recorded lecture will be available, will that class that I missed, will that recorded sessions will be available to you. So I will give you 5 minutes of time after the break, and I will leave you guys to celebrate about it. So celebrate all that you want in those 5 minutes. As of now, let us concentrate on that. I will come back to recorded lecture, together we will celebrate about it. Okay, let's have a deal about it. Now, here, when we talk about the dams, so this huge amount of water which is present, along with the weight of the concrete structure, they will impose very high amount of weight. Many of the times, due to this, what happens that the rock in that localized area, just like an elastic pressure, it gets deformed ever so slightly. For example, if you want to visualize it, think about it, that rocks in this region earlier, let's say they were like this, but owing to the pressure, there's a kind of a localized deformation which you might experience, creating a kind of a bend or a squeeze in the rocks. Now, there are certain kinds of rocks, or there are certain situations where the rocks might withstand that pressure. They might change their shape permanently like this. But also, there are certain structures where the rocks will try to regain their shape. And they're just like in the case of a sponge, many of the times, when you press it, thereby you can press it, but after a point of time, the sponge will try to regain its shape. So imagine the rocks on a larger scale behaving like that. So when the rocks, they try to regain their shape, they try to get back in their original position, they adjust themselves. That triggers a release of energy, which leads to significant amount of shaking and earthquake as well. Now, in certain cases, this is what leads to an earthquake. In certain situations where you build a dam, what happens is, as we have already talked about it, that if suppose this is the rocky layer, then the already the rocks, they are already experiencing huge amount of pressure. On top of that, due to that pressure, sometimes a crack will develop. Maybe the deformation is to the extreme extent, so a crack will develop. The presence of huge amount of water in that region many of the times will lead to a situation where water is able to penetrate ever so slightly in between these rocky joints or rocky cracks. And when water is able to penetrate ever so slightly, that smoothens it and tries to facilitate the movement of rocks with respect to each other. It tries to lubricate the region in between, and that is where there will be a kind of a slippage of rocks. And the slippage of rocks in this region can again trigger massive earthquakes. Example of such kind of earthquake, that is something which was experienced on due to the construction of Koyna Dam. Now, Koyna is a tributary of which river in India? Let me see. Good, very good. Krishna. So you had the Koyna Dam disaster. That was a man-made disaster, so to say, if you can call it, because of the construction of dam. That is why this disaster happened. Then you also have mining operations. Now, when you carry out mining operations, there you have to carry out controlled explosion as well, where many of the times, in order to loosen the rocks, you bring out and install and allow the usage of dynamites and TNT, and you bring about a controlled explosion of sorts. So that also brings about a shaking. All of you belonging from the mining towns of the country, you would have experienced this kind of a feature where in many of the areas you have controlled explosion which happens twice a day, once in the morning, once in the evening, so that enough rocks are loosened and then people can start mining. So mining operations also, due to the aspect of controlled explosion, controlled explosion, that also will bring earthquakes. So this is what is induced seismicity or induced earthquakes. Okay. Now we come to the portion of volcanoes. Mohammed, could you please tell me what am I supposed to write for the question geographic distribution of earthquakes? So, Mohammed, in that kind of a question, you have to elaborate upon that in which areas across the world you have the occurrence of earthquakes. So, you can talk about the entire region around the Pacific Ocean, and you can talk about the plate margins where you experience them, right? So use that map that we have talked about. So thereby you can say that earthquakes, they do occur generally because of plate movements, but also sometimes due to movement across cracks or fault lines. The areas across the globe where you frequently end up occurring earthquakes can majorly be classified into the Mediterranean, Asia, Himalayan region, and then the circum-Pacific earthquake zone. Then each one of them you explain that why earthquakes occur in that region. Then you explain why earthquakes occur in the region of Pacific. Then you also talk about the other areas where earthquakes occur. For example, across the divergent plates, you will talk about that mid-Atlantic ridge, then East Pacific rise, then the ridges which are present all across the Southern Ocean. There also, due to divergences, these earthquakes occur. In each of these cases, try to frame a couple of examples based on current affairs, and that shall be more than sufficient. Just draw the diagrams. Okay. Now, here, now we come to the portion of volcanoes. Now, in the case of volcanoes, I'll give a question for practice later on if you want, but we will be discussing previous year questions tomorrow. So that will give you enough practice. But let's see. Now, when we talk about volcanoes, here, volcanoes are basically the landforms that you observe on the surface where molten materials from the inside or the interior, they are ejected from the surface. Volcanic eruptions have basically shaped not only the ground surface but also our atmospheric realities, and that is what we observed in the portion of evolution of planet. We have looked at it, isn't it? We have looked at the fact that how you had a phase of degasification where volcanic eruption led to the expulsion of materials from inside the earth's surface. Now this keeps on happening all across the planet. Frequently there is occurrence of volcanic eruption. Even if you trace the previous 30 days or 60 days, there also you will come across the occurrence of volcanoes at some region or the other. So there is the occurrence of volcanoes because of various different reasons, but mostly you will observe that volcanoes, they frequent the areas of plate boundaries or plate margins. And in plate margins, what kind of plate boundaries is it that you will experience volcanoes to occur mostly in? So you will observe it in oceanic convergences, oceanic convergences, right? Be it oceanic continental convergence or be it oceanic convergence. In either of these cases, you have volcanic eruption. Then divergence of plates, divergent boundaries, and sometimes you will also come across volcanic eruptions across transform movement of plates. Sometimes also, whenever there is a large crack or a sudden appearance of a very deep crack, there also you will observe sometimes in certain areas you have certain volcanic eruptions which do happen. So that also does happen. So in areas where cracks weaken the crust. So it is in these areas where we experience that molten materials at a very high temperature. They simply erupt out, and after erupting out, while eruption, this eruption is sometimes explosive, sometimes non-explosive, sometimes it lies in between. But in most of these eruptions, you will find that a lot of gases are also released in the process. And the release of gases here, the gases include a variety of different gases. So, for example, you will observe in the gases, you will observe water vapor, you will observe carbon dioxide, then carbon monoxide, then you will also observe SO2. Significantly, ammonia also sometimes is released, but mostly SO2, water vapor, carbon dioxide, this is released into the outside environment. And depending upon how explosive it will also end up emitting a lot of fragments of rocks. small amount of fragments, which is also referred to as tephra in general. So that is also released. And you have in general what is referred to as pyroclastic material. So that includes ash, volcanic dust, small rock pieces, everything that is released higher up into the atmosphere. For example, when you had the volcanic eruption in Tonga, that is the volcanic peak's name was Hunga Tonga Hunga Hapai, that occurred in 15th of January to 2022. Now that eruption, when it occurred, it is estimated, and in fact satellite data that tells us that the smoke cloud could have risen all the way above stratosphere as well, all the way up till a height of maybe mesosphere, maybe at a height of around 80 kilometers above the ground surface. So imagine how much gas is released. The very infamous Krakatau eruption to the east of Indonesia. Where is Krakatau? If I give you some idea, this is where Krakatau is, in this area. So here again, there's a plate movement. Now in 1883, there was a huge eruption which occurred here. The eruption was supposed to be so massive that it is said that the explosion, the impact of it could be felt as far as Turkey on one end and Japan at the other end. So much amount of smoke and gas was released that the entire region around Krakatau, that was where the sunlight was blocked for some time. And it is said the amount of carbon dioxide released in the atmosphere during that eruption, it will take close to around 200 years for the dissipation of all that amount of carbon dioxide. So it releases huge amount of gases, and it is a very eventful phenomena. It is harmful if you are standing right next to it, but in the longer run, it creates new landforms, it provides new minerals to the surface. In many of the cases, it is also responsible for germination of conditions which can lead to the genesis of new forms of life in many of these areas. So that is where it can have multiple impact, right? Now, that is where you have the volcanic eruption. So if you take a look at what are volcanoes, so a volcano is a vent in the earth's crust through which heated materials consisting of gases, water, lava and fragment of rocks, they are ejected from the interior to the surface of the earth. Now it is the presence of gases in general that is something which will bring the materials with a kind of a force. Okay, so if you have to visualize it, think about it. For example, suppose this is the region of the crust. Here you have the molten materials. Okay, now in these molten materials, which is also referred to as magma, so wherever you have the presence of magma, it is also referred to as, and an accumulation of magma, it is also sometimes referred to as a magma chamber. So let's assume here you have the presence of molten materials. Now these molten materials, ideally, they will lack enough pressure to be able to break through the crustal layer. But if you have the presence of gases, gases provide that necessary pressure with which they will simply break through. That is why in many of the areas, in many of the regions in the interior of the planet, even though you have the presence of molten materials, those materials simply do not rise to the surface because there you don't have the presence of gases in the interior. So automatically in those areas, slowly and steadily, those molten materials will solidify in the interior of the surface itself. And when they solidify in the interior, what kind of rocks do they lead to? Or what kind of rocks are formed as a result of it? What do you think? Which igneous rock? Very good. You have the formation of intrusive igneous rock, which is observed in that situation, right? When it starts cooling down in the interior itself. Now, the volcanoes, they are classified on the basis of whether you experience the eruptions frequently, or whether it has erupted a long time back and has not erupted in the recent past, or whether that is a region where you don't experience or don't expect any eruption to happen in the near future. So this is classified as active, dormant, or extinct based upon the frequency of eruption. Based upon the frequency of eruption. That is, how frequently do you experience volcanic eruption to occur in that region? Now, basically, how do we get to know that whether a region is having an active volcano, dormant volcano, or there is an extinct volcano? Based upon the observation that when there was a last eruption which has occurred in that place. Now, mostly you will find that even in the remotest areas of the planet, whenever an eruption occurs, in the large vicinity around it, due to the explosion, due to the materials which are ejected, people get to know. And it always is present in the local account that, okay, there are unconfirmed accounts about it or unconfirmed stories, but there was an eruption which occurred in 1950, or people say, or people of this village say that in 1800s an eruption has occurred. So you will always get a kind of an unconfirmed account. Then based on the sample study of the rocks, you get an analysis and an idea that when these rocks have cooled down, when have they ejected. So you are able to triangulate upon the fact that when is it that the eruption has occurred last. Okay. Now, you can also get an idea about the frequency of eruption or the probability of eruption by studying the regions underneath it. Underneath the volcano, when you study it, you get an idea about how much liquid is present in the form of magma, or whether some part of it is solidified and the magma chamber has got very little amount of liquid present, or whether the magma chamber is completely solidified, as is the case in the extinct volcano, and there is no probability of volcanic eruption happening there ever again. So how do you study that? With the help of seismic waves. So with the help of seismic waves, when you chart out the interior of the planet, you get an idea about the availability of magma in that region also. So in the case of active volcano, you will observe that magma chamber is completely full, right? Example of active volcano in India, if you take the look at the example of it, you have Barren Islands. Where is it situated? It is situated in the region of Andaman. The last major eruption, a big eruption, happened in 1991, then again in 1994. The last eruption happened around 2017. And in 2017, you had the eruption whereby gases were released, some amount of molten materials were released. And in order to understand the intricate relationship between the plate movement and this volcanic eruption, we have talked about one particular date in general in terms of Indian subcontinent, which was very instrumental. That is 26th of December 2004. That is when you had a massive earthquake which occurred in the area around southern Indian Ocean, not southern Indian Ocean, but in the region to the south of Andaman Nicobar Islands, around the region of the western part of Indonesia, right? And that major earthquake triggered a tsunami which caused a lot of devastation. Now, immediately after this earthquake occurred, it was clear that this earthquake has occurred because of the plate movement. Indian plate is subducting underneath, so that is why the earthquake had to occur. But we also know that when you have the oceanic crust which subducts, thereby it can trigger volcanic eruption. And in the days following the December 26th earthquake, you had the eruption in Barren Islands, where frequently Barren Islands kept on erupting. So that again indicated that yes, materials are going to a depth and then they are being expelled as volcanic material. So that is why you will always find a very intricate relationship between the eruptions and plate movements. Now, then example of dormant volcano. What is the example of dormant volcano? Here you can take the case of, yes, Vesuvius, very good. You can take the case of Mount Kilimanjaro. No, Mount Fuji is active. Mount Fuji is not dormant. Mount Fuji, there, because the Pacific plate is subducting, so Fuji is still active, right? It is across this entire area of Fuji, extending all the way till Pinatubo in Mount Pinatubo in Philippines. Those areas are volcanically active. Okay. Then example of extinct volcano, extinct, which has occurred a long time back, and there is no probability of it occurring ever again. Give me the example of that. Mount Kenya, very good. Oregon, very good. So here you have the example of Oregon. No, Hawaii is active. Hawaiian Islands is an active volcanic region. Mount Kenya. Yes, very good. Mount Thielsen. That is where in Oregon you have the eruption. Now, Tonga is again active. So this is the schematic drawing of the volcanic eruption in general. Now, the reason behind the eruption of volcanoes. Why is it that the volcanoes, they do erupt? So basically, it begins with the formation of magma in the lower section of the Earth's crust. That is very much in the portion of lithosphere itself. That is where magma starts to form, either due to plate movement, convergence, divergence, and so on. Many of the times it is also initiated due to the convection current and the convective current which is generated underneath. Now, with pressure, and what provides that pressure? So this pressure that you see is provided by what? The presence of gases. Good. Okay. It is provided by and due to the presence of gases in the region. So because of that, magma travels upwards with tremendous and huge amount of force, and that is when it hits the rocks. And when it hits the solid rocks with a kind of a force, oftentimes the rocks, what will they behave as? They will start shaking. And that is why before a major explosion is supposed to happen or a major eruption is supposed to happen, one day prior to that or a week prior to that, you will observe that in that region there are quite frequent shaking of the earth's surface because of the magma trying to come and hit it. So with every rise of magma, the surface is disturbed, leading to an earthquake. Again another pile of magma rises up. It again shakes the region. Eventually, when it comes with a force, there will be enough shaking, but that is when it will erupt. So in all the major volcanic eruptions, you will observe it was preceded by earthquakes, and very frequent earthquakes. Frequent as in one day you have 15 such seismic events or 20 such seismic events a day prior to that volcanic eruption. So that is where it comes out with huge pressure. Okay. And once the magma reaches the air, that is when we call it as lava. Right. So that is what we refer to as lava in general. Now, this is where the logic with regards to the occurrence of volcanoes on plate boundaries, that is where it stands true. But then we have also talked about the fact that these volcanoes, they don't only occur across the region of the plate boundaries, and plate boundaries convergent, divergent, sometimes even transform, right? So not only across these plate boundaries, But then sometimes even due to the development of deeper cracks, and these deeper cracks, that also leads to volcanic eruption to happen. How and why? So the logic is again very simple here, and it has to deal with pressure. Remember how in the second class we studied about the fact, not in your second standard, in the second lecture of this module, we discussed about the fact that due to the huge pressure which is exerted, the inner core is in solid state because there is so much amount of pressure that it has got no place to expand. So there is an intricate relationship in the case of the interior of the earth with the melting point and the pressure exerted. Okay, how? So for example, suppose this is the crust. Let's suppose this is the lithosphere. And here you have certain materials which are present. Let's say iron, magnesium oxides which are present. Let's assume any kind of material. Now, normally we know that due to geothermal gradient, as we start going in the lower portions of the surface, the temperature starts to rise up. We are aware of that fact, isn't it? So here again, as we start going lower, the temperature will go up. So let's assume the temperature, I will write here, let's assume, otherwise I understand many of you get fidgety that how do you know that much is the temperature, have you gone there? So let's assume, okay, temperature in this region is 1000 degrees Celsius, assuming, okay, please don't ask me what depth are we talking about, at what time of the day are you talking of. Let's assume in general the temperature at this depth is 1000 degrees Celsius. Now simultaneously let's assume the melting point of the material that you see here, that is 1050 degrees Celsius. Again, let's assume. So in that situation, will this material be present in solid or a liquid state? Easy. No need to apply even some part of your brain here. Very easy. It will be in a, oh, okay. So looking at the answers, let's get the answers. So if the melting point is 1050 and the temperature at that region is 1000 degrees Celsius, will it be available in solid state or liquid state? Hmm. I thought everybody will get it right. So tell me one thing. When we talk about two temperature, 1000, and leave all this image, obviously it is complicating your concepts. 1000 degrees Celsius and 1050 degrees Celsius, which is higher? 1050 degrees Celsius is higher. So if the temperature in that region is 1000 degrees Celsius, how will it melt? It will not melt. So it will be in solid state, isn't it? So again, use all the logic that you can. It will be very much in solid state because the melting point is higher, right? Now, in that case, here it will continue to remain in solid, but let's suppose due to the movement which is happening in between the rocks, in between the plates, that is where any kind of movement which is happening, thereby let's say there is development of a crack which has appeared. Occurrence of cracks. Now when there are occurrences of cracks, let's suppose, then what happens to the pressure which is already being exerted on it? The pressure will reduce, remain the same, or will it increase? What will happen when suddenly above it all the rocks they develop a crack? It will obviously be reduced, right? The pressure that was being exerted, that has suddenly been reduced. Now when the pressure has been reduced, what is the consequence of it? Thereby you will observe that the materials, they get a scope to expand easily. So the melting point tends to reduce. So when you have occurrence of cracks, that leads to decrease of pressure. And that decrease of pressure, what does it do? It basically lowers the melting point. Melting point. So here, the melting point, which was earlier 1050 degrees Celsius, if I say that it has been reduced and it reduces to 950 degrees Celsius. Now, when it has reduced to 950 degrees Celsius, obviously it is much lower than the ambient temperature. So thereby, after this material that will start melting in this region, you will have, for example, if we had assumed that you had iron oxide, magnesium oxides, so the oxides, etc., they will start getting released as gases, and that is when you will have the presence of molten materials along with the gases that can simply break through these areas. So in many of the portions of the planet, you also have volcanic eruptions which are experienced due to development of very deep cracks, and these very deep cracks, they lower the pressure, and due to that, in the lower regions the melting point is reduced, due to which molten materials, they rise up. But it is not observed in all the cases. It is not as if wherever there is a crack which has appeared, there is going to be a volcanic eruption, but it can definitely happen. Okay. Now, then we come across to the types of volcanic landforms. What are the various different types of these landforms? So here, when the volcanic eruption happens, you have various different types of materials which are expelled. And these different types of materials, they spread to larger areas as well. Right? Now, it depends upon the type of materials. So generally, the molten materials, when they are present in the interior, we refer to them as magma. We refer to them as magma. Now here, magma is in molten state, but it can have various properties. Not all the liquid has the same property. Certain liquids, they are able to flow easily. Certain liquids, they basically flow very slowly. They have a very lesser flow. For example, take the case of water and honey or nectar. So honey, that flows very, very slowly, whereas water can flow very easily. So based upon the flow, you have the viscosity. Now here you have viscous magma. Viscous magma is the one which does not flow easily, and non-viscous. Right? Non-viscous means easily. Its ability to basically flow. Now, let us apply again our common sense and common logic here. Suppose I have a particular region on the crust. Let's suppose like this. This is connected to the magma chamber. Let's assume. Let's assume this is connected to magma chamber. Now here, if we assume that there is presence of viscous magma, that means it doesn't flow easily. So for that magma to come out or to bring that magma out, do you need less pressure? Will you be able to manage with less pressure, or do you need high amount of pressure to bring that sticky magma out? Let me know what is needed. Very good. High amount of pressure will be needed because it is very viscous, it is sticky in nature, so you need greater force. Now that pressure is brought about by what? By the presence of gases. Now in the presence of gases, in the presence of that high amount of pressure, you have the viscous materials which will be brought out. But when these materials, they are coming out, obviously they will come out with huge pressure, because that is only when they will be expelled. Now, that is why wherever you have viscous magmatic eruption, it will always be explosive in nature. It will always have a kind of an explosion which happens, right? That is where you will find that viscous magmatic materials are always expelled in the form of explosive eruption. Whereas when we talk about non-viscous, that is something which flows almost like water, something that you observe in the region around Hawaii, right? The Hawaiian Islands. If you observe the volcanic eruption, and you can basically look at it on YouTube as well, where you have large videos which are available, or long videos which are available with regards to how the magma behaves in Hawaii and how there's a continuous flow. It gives you an appearance as if there is a waterfall of sorts of lava. That is how fluid it is. Now, if the material is that fluid, you won't need that much amount of pressure. So it can come out even in the minimal amount of pressure. So that is when generally I am using, generally non-viscous magma will be expelled in a non-explosive eruption. Viscous magma requires explosive eruption. Now, depending upon the type of eruption which has occurred, you have the various landforms: cinder cone, composite volcano, or the stratovolcano as it is referred to, shield volcanoes, and also what we refer to as lava domes. There's a further subclassification of volcanoes on the basis of eruption. For example, you have the Strombolian eruption, you have the Strombolian type, you have the Pelian type, you have the Hawaiian type, you have the Icelandic type. So, not all of them are important for you for general studies. In fact, none of them are important for you for general studies. Few of them I'll let you know, or we will talk about when we have the discussion for these landforms. So, we start with the first of its kind, that is the cinder cone volcanic eruption. Now, in the case of the cinder cone, cinder means what? It is an English terminology. So, cinder, the meaning of it translates into something to deal with fire, right? Incendiary. That is what you use, right? Incendiary speeches were delivered, fiery speeches were delivered. So, cinder always has to deal with fire. So, cinder cone, so here you have molten materials which are expelled, and it is an explosive eruption, right? So particles and blobs of lava are ejected from the volcanic vent, and this is generally an explosive eruption. Explosive in nature. And another thing, before any of you get confused in this, or before any of you, just by looking at these images, you start developing a concept and you ask a question, why volcanoes emerge only in the case of mountains? Let me make it very clear. It is the eruption which creates these volcanic mountains. In the initial days in these areas, what would have happened is that you would have had the presence of a weaker crack on the ground surface. And slowly and steadily, you would have molten materials coming out of those cracks. And that is how molten materials initially would have settled around these cracks and solidified. More materials would have been expelled, and that is how this region would have gotten converted into a kind of a conical shape. Okay, and that is how you have the volcanic mountains as well. It is not that volcanoes emerge or erupt in the case of mountains. Volcanoes create those mountains, or the solidification of magma or lava in general. That is what creates these mountains. So the lava is blown violently into the air, and the pieces they rain down after being blown violently, they will fall down, they will stick to places, they will solidify, and that is what eventually ends up forming a kind of a conical structure at large. Now, over time, this builds up a circular or oval shaped crater on top over time. And this circular shaped crater which gets created, that is what is also referred to as a volcanic crater in simple terms. These cinder cone volcanoes, they are not very large in size, in terms of cross section, in terms of height. It is not as if they are very large, right? Generally, you will find that they have a height of only up till around 1,000 meters above or beyond their surrounding regions. That is the height that they have. Okay. Now, after this, we come to the portion of composite volcanoes, right? We will take a look at what do we mean by composite volcanoes. So, composite volcanoes, these are also what are referred to as stratovolcanoes. Okay, a confirmation, by the way, the audio is available. Just confirm that. Perfect. So, for all those whom it is not available, kindly reconnect. Right. Now, then we talk about the composite volcanoes. These are some of the largest volcanic structures that you will come across. And these are large not only in terms of their size, in terms of their cross section, but overall you will find multiple different peaks emerging in this area. So, they are some of the Earth's grandest mountains and are also referred to as stratovolcanoes. What is this term stratovolcanoes? Here, the term that you have to look into is strato. Strato is derived from the term strata, which refers to layers. So, in this, you have a kind of a layered structure. So, generally, stratovolcanoes or composite volcanoes are the ones where you will find different types of lava that is thrown up, or different types of magmatic materials they are thrown up. They can be andesitic, they can be basaltic. So, all of them of different densities, they are periodically and regularly expelled into the atmosphere. So, here, for example, let's suppose this is the volcanic vent which develops. Then around it, you will have solidification slowly but steadily. Let's suppose initially you have basaltic magma, then you have another type, the lighter density one, andesitic. Okay, so then again you have, let's say, basaltic. So, over a period of time, that develops multiple different layers, and that basically brings a large area under that volcanic region. And it is a very large landform which also develops. Now, here you will observe that whenever there is that expulsion of materials, ash, dust, small tephra, pyroclastic materials, rock fragments, all of them, they are also expelled. Now, those fragments, they will settle down. So, they will settle down on top, bring about a layer of deposits. Then again another eruption happens, that will lead to molten materials depositing on top of that ash. So that is how various different types of strata or layering is developed. Now over a period of time, here if you look at it, let's suppose this is a kind of a stratovolcano, with this being the original volcanic vent. Original volcanic vent, let's suppose. Now, it is not necessary that the next time the eruption will happen, it will happen from the same vent. Why? Because there are chances that the materials would have solidified in that vent. And that is where this vent over a long period of time would have become very highly compressed solid rock, which would be very difficult to break. So in that case, the molten materials, they start breaking from the weaker areas, wherever the weaker areas are present, and they will erupt out of the weaker areas. So that is what is also referred to as sometimes parasitic cones. Why parasitic cones? Because they are fed from the same magma chamber, but they are not the main vent. They are the side vents, so to say. So that is why, because the magma chamber is same, hence they are referred to as parasitic cones. Example of stratovolcanoes, you will find multiple such volcanic eruptions in the region of Reunion Islands in southern Indian Ocean. Other examples, you have Mount Shasta and Shastina. Mount Fuji is also an example of a stratovolcano, right? So you have multiple such examples of stratovolcano. Shastina is a parasitic eruption of Shasta. Krakatau used to be a stratovolcano, but now it has turned into a caldera because the central portion has simply subsided. That is why it has now turned into a caldera. Okay. Yes, Reunion Islands will also have many different types of composite volcanoes which are present. Then we come across to shield volcanoes. So the shield volcanoes basically, here their shape is almost flat and featureless. So that means the molten materials would have spread to far off distances and would have flown very easily. So that means if you take a look at the magma which would spread, the magma which would immediately erupt or be expelled as lava, that would be viscous or non-viscous in this case. What do you think? Very good. It would be non-viscous. So here you would have generally non-viscous or fluidic lava, which is expelled in the form of a non-explosive eruption. Non-explosive eruption. Okay. So that is what you observe in the form of a shield volcano or the dome volcano in certain cases. Now this shield, it spreads, and over a wide area it flows and it spreads, and thereby it solidifies eventually, and after that it will give you a kind of a flat and a featureless kind of an appearance. It will not have a sudden steep height, but rather resembling the old shields that you used to have, that kind of a feature for topography you will observe. Examples of this, examples across the globe, if you will take a look at. So you have Canadian Shield, this is not chiseled, by the way, this is shield. Okay, Canadian Shield. Then you have Hawaiian. In Hawaii, you have what kind? Yes, you have Mauna Loa, or simply we can write here Hawaiian Shield. Then you have the Deccan Trap in India. So in almost all of these, you will generally find that basaltic lava is expelled. You have the basaltic lava which comes out as a result of almost all of this. Okay. So they have very gentle slope and are developed horizontally, that is, they spread out horizontally. Shield volcanoes are built by effusive, that is, non-explosive eruptions which flow out in all directions. Then we have the smallest of all these structures in a way, that is referred to as a lava dome. Now, lava dome does occur or is observed when you have extremely viscous lava, which cannot flow, almost which has the inability to flow. So in that case, immediately as the molten material emerges out of the cracks of the volcanic vent, it will solidify as it is wherever it has emerged. And thereby, it will create a kind of a solidified viscous lava structure that resembles the shape of a dome and hence referred to as lava dome. Okay. Now here, when you have more and more molten materials which try to come out, basically this lava dome will emerge and will try to expand in size from inside. But then here you don't have very explosive eruptions or many different eruptions which happen here. Very viscous magma or molten materials, they simply solidify. Then we have the fissure volcanoes. Yesterday also we took a look at fissure volcanoes, and day before yesterday as well. So when we talk about fissure volcanoes, these are generally observed when you have large cracks which open up on the earth's surface, very large cracks which open up on the earth's surface. And these cracks are generally observed across divergent plate boundaries. Generally observed across divergent plate boundaries. Okay, generally observed across the divergent plate boundaries. Now, that is when multiple vents open up, multiple different vents open up across a larger crack, and molten materials simply come out. This is something which is very, very prominent across the region around Iceland. And that is why this kind of an eruption is also referred to as Icelandic eruption. Icelandic type of eruption. So, this is how it takes place, a kind of a recreation of sorts. They are so formed due to slow upwelling of low viscous magma. So, here also, if it is spreading out easily across the surface, obviously it will not be viscous. It will have very low viscosity. So, along a fissure or a crack, when it starts spreading, that is when you have a fissure volcano. So, the resultant lava is spread over the ground surface. Sometimes it is also referred to as Icelandic eruption. Okay. Example of this, you take the example of Trevera eruption. Where is it that you observe this Trevera eruption? In which portion of the world? No. No. Think about it. Search about it. In the region of New Zealand. Then you have Laki eruption in Iceland. Laki eruption is the most famous one. Okay, so these are the examples of fissure eruptions. Then we come across calderas. Now, these are some of the largest landforms that you will come across. And these calderas, they are created generally in the last stage of a volcanic eruption. It is not as if in these areas fresher eruptions will not happen, but this is something which is observed when you have the emptying of the magma chamber, generally formed during the emptying of magma chamber. Formed due to emptying of magma chamber. By the way, that magma chamber can be refilled again. It is not as if in this area there won't be any further volcanic eruption. That magma chamber can again be refilled. Okay. But how is it that this caldera is formed, and what is this caldera exactly? So generally, in many of the areas across the globe, generally across the oceanic regions, for example, when we talk about the Tonga eruption, for example, when we talk about the Krakatau eruption in the region around Western Indonesia, when we talk about the great calderas in the region to the south of Greece, all these are those areas which are very, very large and seawater has entered inwards. So let us try to understand what these generally are. So the image indicates to you the existence of a caldera. Don't mistake it to be just a kind of a mountainous lake. Calderas basically here in normal, when you think about a volcanic landform, what do you think about? What is the first imagination that comes to your mind? That it would be kind of somewhat like this kind of an eruption, or this kind of an a landform would be there. That is the normal imagination that comes to your mind. In the case of calderas, you have a landform which resembles somewhat like this. And this is something which is basically filled with water. This water can basically be ocean or sea water penetrating in this area, or sometimes even groundwater rising up in this area, rainwater concentrating over a period of time. But generally, you have seawater coming in. So, this is filled with water. So, this entire thing is referred to as a caldera. Lonar Lake is not a caldera. Lonar Lake in Maharashtra is special because it is a lake created because of meteorite impact. And in fact, all across the globe, it is the only basaltic rock or the only evidence of how a meteorite can influence a basaltic rock. That is why Lonar Lake is special. It is not a caldera, however. There are evidences of calderas in the region to the north of Aravallis. When you drive away from Delhi in the region around Gurgaon, Manesar, Pataudi, in those areas, there are some evidences of ancient calderas which are many, many million years old, right? In even billion years old. So let us understand how this is created. So this starts with an explosive eruption. So suppose now this magma chamber is too huge. So let's assume this is the magma chamber. Now here, when the eruption is happening, you have molten materials from the magma chamber which are expelled out. Now imagine that in the last phases of eruption, last stages or phases of eruption, that is during emptying of magma chamber. Now, in this case, many of the times you have very explosive eruption. For example, take the case of example 15th Jan 2022 eruption at Tonga, that is South Pacific. The name of the peak, Hunga Tonga Hunga Hapai. So that is where you have a very explosive eruption which occurred. Now, when there is a significantly explosive eruption which will happen, this entire thing will weaken. It will start developing cracks, isn't it? So there will be development of cracks in the structure of the mountain because of that huge explosion which has happened in the mountain. Obviously, the mountain will develop cracks, the weaker points, the weaker joints. And now the magma chamber is empty. So now the empty region underneath, will it be able to take the entire weight of the mountain above it? Obviously not. So that is where the heavy portion above it, that simply starts to sink. It simply subsides or collapses in that region. So because of the emptying of magma chamber, empty magma chamber, what it leads to? Leads to a collapse of the structure above. And that is when, from that weak area, everything which has been in a way dismantled due to the explosion, everything simply subsides or collapses. So what you are left with is a kind of a remnant. So what you are left with is a kind of a remnant of what earlier used to be a very large volcano, but now all that is left behind is a kind of a remnant. And this is where water fills in. Generally, this is this kind of explosive eruption you observe wherever you have the oceanic areas. That is where you have these kind of explosive eruptions which occur. Okay. And that is when you have the ocean water or the sea water which penetrates inward. So Tonga, Krakatau in Indonesia, Crete in the south of Greece, all these are examples of calderas. This also, what you see in the image, is a caldera. So imagine at one point of time, this would have been one large mountain, a large volcanic mountain. The top of it has simply collapsed underneath. Okay? Yes, seawater comes from the oceans behind. How seawater reaches in caldera, that is when the eruptions, if they happen in oceans, that is when the seawater comes in. It is not as if the eruption is happening in the middle of the continent and seawater is rushing in, crossing all the various continental lands, that okay, there is an eruption, I have to go there, I'm in a hurry. No, nothing like that, nothing of that sorts. Seawater will get in only if there is an eruption happening in oceanic region, and when that collapses, obviously from the surrounding region there will be the seawater which gets in. Okay. Now, can calderas erupt again in future? That completely depends on the plate movement in that region. If the plate movement continues and there is continued subduction, you might have materials which go down, lead to the creation or the further creation of molten materials. So it can always happen. Okay. Okay, all those who are getting really confused about seawater, that where is it that seawater is coming in? Let me be very clear, guys. When I say seawater, please don't think that an eruption will occur here and you will have seawater coming into this eruption and forming a caldera. Please don't think about it. Okay, that is not at all the situation. If when we talk about Tonga eruption is happening here. So in the middle of the ocean. So Tonga eruption, when you talk about Tonga eruption, what does the Tonga eruption look like? If you have to draw it out, suppose this is the sea floor, this is the sea surface, and this is the Hunga Tonga peak, let's suppose. Now, if this structure will collapse, let's suppose this is the structure which collapses. So if this structure collapses, then you will have the formation of a structure somewhat like this, which will be slightly depressed. Now, what will happen in this depression? The surrounding seawater slowly will come in. During the explosion itself, many areas will be submerged in seawater. That is where the seawater comes in. It is not as if the eruption is happening in between here somewhere and seawater is rushing in that, okay, I have a task at hand. No, nothing like that. That is why I've given the example of Krakatau. I've given the example of Tonga. I've given the example of Crete. So these are where these calderas exist. Okay, right? Now, after this, we come to the portion of the mantle plumes. But before that, we'll take a break and then we will talk about mantle plumes, hotspots, and then the various aspects with regards to the type of magmatic material, how it determines a type of eruption. That is something we will talk about after the break. Okay. So break will come back at around 7. Okay. And then we will continue. A confirmation regarding the audio, please. If you're able to hear me out perfectly well, kindly confirm. Thank you. Hot springs are basically when you have, in certain cases, the water, groundwater, when it comes in contact with the molten materials or superheated rocks as well. In certain cases, that can lead to the generation of hot springs and geysers. Yes, Prasan. As a result of that, the movement of the Indian plate was further accelerated because of that. Okay. Sayadri, I have attended your class in December. Have you made changes in this batch? Yes, I have made changes in this batch. I have changed the contents of the PPTs in this batch. And see, there are portions which keep on getting updated. So that is where there are new things which have been brought. There are older things which have been eliminated as well. So as we move ahead in the portion of climatology and so on, few of the older things will be eliminated. The newer things which are in relevance, which are in discussion, that is something which will be brought in. So that is something which is a constant process, but majority of it is going to remain similar. Composite volcanoes, basically, see, composite is the name which is, so think about the English meaning of it, Sachin. So composite means oftentimes the eruption, when you consider it a large period of time, in that you have multiple different types of eruption. So you have, for example, the eruption of basaltic lava that will spread, then andesitic lava, which is granitic lava of sorts, so that will accumulate, then again a basaltic lava. So overall, it is a composite of eruptions. But at the same time, this entire process creates multiple layers, and hence it develops multiple layers, and hence it is also referred to as stratovolcanoes. Okay. In the case of dams, how does development of cracks lead to? See, when you have the development of cracks amongst the rocks which happens, use your logic here. So if suppose the rocks have developed a crack and there's a pressure induced on top, automatically the rocks will try to slide. So even if there is a slightest of slide of maybe 1 centimeter or 10 centimeters or maybe a couple of meters, imagine the disturbance that it will create on the surface. So that is what induces earthquake. Shield volcano, Shamil, is basically when you have the eruption or the expulsion of fluidic lava and it spreads in all direction. It gains a kind of a shape of a shield, right? The shield and sword, if you can visualize. So the shield is pretty featureless. It emerges or gives you an appearance of a kind of a large dome of sorts. So that is a shield volcano. Tsunami will happen only for oceanic plates, Rohan, not necessary. In the case of oceanic continental convergence also, but oceanic plate needs to be there, because please understand, if the Indian landmass is colliding with the Eurasian landmass, where will the waves be generated from? There is no water on top of that. So you need to have an oceanic plate into consideration. Karthik, is all empty volcanoes converted to calderas at last stage? Absolutely not. Tsunamis only take place because of earthquakes? Not always so. Sometimes very explosive volcanic eruption can also disturb and lead to the occurrence or generation of large waves. Sometimes in coastal areas, you would also experience, particularly in the region around Antarctica, Arctic, etc., where you have large glacial sheets which simply fall into the water. That also ends up generating mega large waves. So sometimes slides, rock falls, sometimes even when you have earthquakes. So multiple events can lead to generation of big waves. Tsunamis are nothing but extraordinarily large waves. Okay, calderas exist only in sea regions, mostly in sea regions, but not always. Yes, Candy, PYQs will be discussed relating to geomorphology. And for all those of you who are worried about that, whether this will be done or not, everything will be done. Don't worry. Okay. Is tsunami happens due to the large amount of water vapor from the broken crust? Absolutely not. Why frequency of earthquakes in some area is greater than the others? Because in certain areas the plates are moving regularly, in certain areas the plates have not indicated a motion for a long period of time, so that changes. Okay, see, all those who are in undergraduation or you have some time for your preparation, there can be two approaches which can be taken. One approach, which most majority of the candidates, the one approach that they take is that, okay, there is enough time which is there for the examination. This year I will do only this, next year I will do this, year after that I will start reading newspaper, year after that I will initiate new answer writing. And what happens by the time that the examination year comes, you have neither done that nor done that, and you have forgotten everything. So that is the route that majority of the candidates will take, close to 99% of the candidates will take. And you should be aware of this reality. What you have to create a difference here is that if, let's say, you have 2 to 3 years before your examination, don't target the fact that I somehow have to get through it. I have 6 attempts in front of me. No, in first attempt I have to clear this examination because I have gained such an advantage over the competition, because I have initiated so early. So my aim, my dream has to be bigger. I have to ensure that I get through within or under the age of 25 years at max. All those who are in undergraduate or doing your graduation right now. So target double digit rank. So for them, right now, current affairs should be started, general studies should be focused on, finish the general studies, then within around 6 months to you have to initiate any optional that you are studying, start studying that optional. And that aggressive approach, that is needed, because please understand, 4.5 to 5 lakh candidates will appear for the prelims, almost around 60 to 70,000, if not more. They will be the ones who have studied all the books that you have studied, at least those number of books, if not more. So the competition is huge. There, nobody is going to ask you that what was your timetable, how much you have struggled, or so on. Nobody is going to bother about that. But then, that is where, if you have to create a difference, the early starters, you can create a difference. So don't allow complacency to creep in. Okay, now here, coming back, now we talk about the aspect of mantle plume. Plume, again an English term. In fact, across the entire subject of geography, wherever you come across any phrases or any terminology which does not make sense to you immediately, and this will happen, UPSC does like to throw surprises here and there, and it will throw you certain types of terms which you might not have heard anywhere else. But then the key at that point is not to panic, but look at the English translation. What is the English meaning of it? And chances are you will be able to understand the phenomena to the closest of the possibility. So when we talk about mantle plume, even without knowing what it is, we can tell something about, or some properties and some features about it. For example, it will be present in the region of mantle. That is why mantle plume. Otherwise, we could have called it crustal plume or core plume, but it is mantle plume. So it is present in the region of mantle. What is a plume? Plume is generally a rising column of heated material. You have plumes of smoke which rise up. That is where you will find the usage of the term plume in English vocabulary as well. Recently, Kochi, the region caught the you had a lot of garbage in that region which caught fire. So you had plumes of smoke which was rising. So that is where plume is used. So here we can translate it literally into the form of something which is very hot, which is, or hot material which is rising up vertically, and this is happening in the region of mantle. Okay, now this entire aspect of mantle having that rising column of heat, this is something which we were not aware of up till the 70s. And in fact, even though the convection current theory was provided way earlier during the 1920s, nobody was aware that yes, you had consistent rising columns of materials which were rising in the region of mantle. So basically, if you take a look at it, this is how the mantle plume appears to look like. Obviously, it is an artistic recreation because nobody has had the guts till now to cut the planet in half and take a picture of the mantle plume. Simply impossible. So obviously, artistic recreation is the best that we can do in that case. Observe how you have excessive heat which starts rising up via the materials, and it gains a kind of a bulb like shape. It gains a kind of bulb like shape. So these are your mantle plumes. So these are basically generated due to what? Generated due to convective current. Currents in the mantle. Now, what is the source for the generation of these convective currents? So, as I told you, the entire logic of mantle plumes was something which was discovered in the 70s. And by that point of time, our understanding was slightly restricted. And that is where all the geographers of the time, they basically confided on the opinion that this convective current is generated due to the heat provided, excessive heat provided from the region of outer core. So this is generated due to excessive heat provided from outer core. Now, what is this heat referred to as? That excessive heat which is present, what is it referred to as? Let me know. Very good. See, like this, I will keep on asking you time and again, and I'm going to force you to recall it. Okay. So, this is not residential heat. Come on. It is residual heat. Residential is something which lives there. Residual is something which is left behind. So, that is your residual heat. So, overall, if you have to think about it, then imagine this to be the surface, this to be the portion of the crustal layer, right? Let's suppose, or the lithosphere, if you want to consider this, suppose is the region of mantle. This is the outer core, the liquid outer core. Now we have discussed it already that you don't have the condition where consistently from one region heat is supplied or uniformly from all areas heat is continuously supplied. No, the heat is emanated from some region for a brief duration of time or for a long duration of time. Obviously, the brief duration and long duration that we are talking about in geographical terminology, not in terminology of ancient, medieval, and modern history, which can be confined in few years. When I say brief duration of time, here I am talking about few thousand years or 100,000 years. When I say that a longer duration of time, I'm talking about a few 100 million years. So for that duration, you can have maybe an excessive heat which is provided from this particular point, let's say, right? So it will start melting materials immediately here. Now the molten materials which will be superheated, they will start to rise, they will try to rise because molten materials in general are lighter as compared to the solid materials. They will try to rise. As they try to rise, they will start melting the materials above them as well. So they will start melting. So that is how you have a rising column which is observed. And it takes the shape of a bulb-like head on top, right? So you have a rising column. Now this rising column, it is not supposed to exist in the same place always. It might happen that 200 million years from now, this region might not have any more heat which is produced in that area, or heat might be generated from some other region altogether, or from some other place altogether. It can absolutely happen that you can have a situation where excessive heat is produced from this area. Now heat has dissipated from this region. So now there is no more heat produced from there, but maybe another heat which is produced from here, let's suppose. Now, as a result of that, you have generation of plumes. And these plumes, they rise up. Now, these plumes, when they start rising up, what will happen? So they will overall rise up. Now, when they reach the region of the lithosphere or the crustal portion, that is where they will be able to create a large section of molten materials, very large areas of molten materials, and it will create super large magma chamber, and thereby these materials, they will rise up and lead to volcanic eruptions in a place. Okay, so they will lead to eruptions. Okay, I will repeat. So you have excessive heat, the residual heat which is trapped in the region of the outer core. Now that heat is transmitted in the region of the mantle from various different points, from various different portions, and thereby the portions of the mantle, they start melting and they start rising up, creating a rising column which we refer to as a mantle plume. Now the magma chamber that you see here, this magma chamber, do you think it will ever get emptied as long as the mantle plume is there? No. As long as the mantle plume here exists, this magma chamber will always be full. So that is why in the areas of mantle plumes, you will experience continued volcanicity or volcanism going on for hundreds of years, thousands of years, millions of years altogether. So in the regions, in these areas, the molten materials or the magma chamber is consistently refilled, leading to continued eruptions for millions of years. How do they rise? They rise because of the excessive heat, because as the molten materials, let's suppose there is heat produced, so in this region the materials in the mantle, they will melt because of that heat. Now because of that liquid, we know that liquid is lighter than solid, it will have a natural tendency to rise up. But along with that, you also have to consider that this heated liquid is consistently provided with heat from underneath. So it will start melting materials above it as it starts to rise. So always you will have a condition where this rising column will start melting more materials along the way at the head of it, and then it will rise further. So that is why you will observe the development of a kind of a bulb-like feature. This is where in the region of the bulb-like feature, it starts melting the materials overhead. When those are melted, then it rises up further, more heat, because consistently heat is being provided from the inside. Now, this mantle plume, Basically, for a long period of time, it was understood to be provided only from the region of outer core. It was only later on that the realization came in, and various research papers were published in the late 1990s, the early 2000s, and as late as up till 2015. The researchers finally concluded upon the fact that this huge amount of heat is not always a resultant of the from the outer core. Here, they came upon the realization that this convective current can sometimes be generated where? Even in the region of asthenosphere. Region of asthenosphere. That is somewhere situated in the upper portion of mantle. Okay, let's assume this represents the region of asthenosphere. So sometimes even in the region of asthenosphere, due to excessive heat produced, there can be generation and existence of a kind of a convective current. Now, or the mantle plume in general. Now, whenever this mantle plume comes into existence, not only will it lead to frequent eruptions which can last for a very long duration, but it can also induce, this rising column can end up inducing a convective current. Okay, so the rising column of heat, the rising column of heat in the mantle can generate convection currents. In the mantle. Now, when you have the generation of convection current in the mantle, what is it that we experience on the ground surface? We experience plate movement, divergence of plate, convergence somewhere else, subduction of plates, transform movement of plates. So this can generate or leads to movement of the plates. Leads to the movement of the plates. In general, you will observe that mantle plumes, they don't have a long extent. That is, in general, it is not as if all across the Atlantic Ocean or all across the African Rift Valley you will have the mantle plume. Mantle plumes, they are generally concentrated in size and the point of impact. Right? For example, if you take the case that where you experience mantle plumes, example can be Reunion Islands. Where are Reunion Islands? You have them in Southern Indian Ocean. Southern Indian Ocean. Mantle is not in liquid form, my dear friend. Kindly take a look at it. Mantle is in very much in a solid form. Only a section of mantle, asthenosphere, that is also not in liquid. It is in semi-solid or a plasticky state. Okay, so Southern Indian Ocean. Another one. Yes, Abhinav, very good. And Dinesh also, very good. So another one, example, good, Sumit. So this is Hawaiian Islands. in the region of Pacific Ocean. Mantle plumes are not in gaseous state. It will have some gases trapped along with it as the materials they start to melt, but it is in fluidic state. It is in liquid state. So that is where these mantle plumes can give rise to plate tectonics and plate movement as well. This is the definition that is most valued by many of you, that regardless of whatever you say, provide us the definition. So this is the definition. So mantle plume is the convection of magma in the narrow columns in upward direction from the core mantle boundary, forming a mushroom-shaped cap to the plume. Now, mantle plume magma is hotter than the surrounding magma. Why? Because it is consistently being provided with heat or the residual heat. So, why is that the case? Because of consistent provision of heat. From interior. And position of mantle plume is supposed to be fixed in certain areas of the globe, and that is where, for example, Reunion Islands, Hawaiian Islands, they keep on coming up. Who had seen the mantle bulb like structure? Thankfully so, nobody has been fortunate enough to go deep into the mantle, and that is where all of this is based upon the projection that we make, the calculation that we make by studying the seismic waves, that where you have the molten areas. In many of the cases, in case you are interested to know, in case you are genuinely interested to know, whenever a volcanic eruption happens, even though that region is evacuated, but you will find that immediately that region is crowded and flooded with geologists and also chemists. You have a lot of chemists who reach there along with the geologists. Now they take the sample of the rocks and they study and examine the molecular arrangement in the rocks. By studying how the rock has solidified, they can gain an idea, they can calculate that for how long this has remained in liquid state, at which depth has it remained based upon how much pressure this molecule has experienced, and thereby they come upon a conclusion whether this molten material has emerged all the way from the bottom of the mantle or it has come only from the region of asthenosphere. So that is how they get an idea that, okay, this region, this particular rock that we see, this has spent a lot amount of time in a particular area in the portion of the mantle, middle of the mantle, let's say. So there you get a clue that, okay, why this would have emerged, because there's a mantle plume there. That is how you come to these conclusions. Okay. Now, then we come across to hotspots, volcanic hotspots. So, what are volcanic hotspots? Hotspots in general are those events where the frequency of occurrence is very high. So, when we talk about volcanic hotspots, these are those areas across the planet where you have very high frequency of volcanic eruptions. Generally, these are the ones which exist over the region of the mantle plume. So a hotspot is a volcanic area on the earth that exists over a mantle plume. Okay, now because of the fact that it exists over the mantle plume, you will have the magma chamber which is consistently refilled again and again and again. So as the magma chamber is consistently refilled, it will lead to consistent eruptions and significant frequent eruptions, which is going to happen there. So those are referred to as volcanic hotspots. Example, when we talk about it, example we can take as Reunion Island hotspot, where in Indian Ocean, then Hawaiian Island hotspot, hotspot. Now, wherever these hotspots they exist, they leave behind a chain of volcanic landforms. How? So, the mantle plume basically fills up the magma chamber in the region around the lower portion of lithosphere and the upper portion of asthenosphere in general. The plate movement happens on top of that. So, if you have to think about it, suppose if you consider this, let's suppose this is the surface. So, here, yes, almost every mantle plume will have a hotspot. So suppose this is the surface, and here you have a large magma chamber which is supported by a mantle plume. So always consistently it is filled up. Now here you will observe an eruption of sorts, a volcanic eruption. But then this can continue for 100 years, thousands of years, hundreds of thousand years, maybe few million years also. But eventually, the surface, which basically constitutes some or the other plate, eventually it will move, right? So let's assume the plate is moving in this direction. So when the plate is moving, the volcanic landform on top of it, that will also exhibit a kind of a motion, isn't it? So let us assume that the volcanic landform along with it, that has also moved ever so slightly. This has also moved ever so slightly. So when this has moved, sometimes what will happen is that it will still have a kind of a contact from the main magma chamber, and that can lead to certain eruptions even in the older landform. But then mostly the magma will erupt out of the main vent and create a new landform, isn't it? But over a period of time, maybe 100,000 years later, right, 1 lakh years later, that is, the plate again moves slightly. And when the plate again moves slightly, so all these, they will further shift. The contact will be broken. They will further shift, right? So the earlier eruptions that you had, you won't experience eruptions there anymore. You will have a newer eruptions. So these are your oldest eruption. And this is your newest eruption. Now all this is getting supplied from the same magma chamber. All of this is getting supplied from the same magma chamber. And when it is getting supplied from the same magma chamber, this is what is referred to as a volcanic hotspot. And just by looking at the chain of volcanoes or the landforms created, you get an idea about in which direction this is moving. For example, if you take a look at the Hawaiian hotspot in the region, basically the mantle plume underneath Hawaii, that is what, in a way, is filling up the magma chamber. This is your magma chamber. Right? Now observe the image carefully for a moment. So here you will observe that now eruptions are happening here. That is the Hawaiian Islands. And that is the present day hotspot. But then the oldest volcanoes are where? Here somewhere. Then you have the eruptions happening 5.1 million years ago here. Then another eruption 2.6 million years ago here. Then 1.8 million years ago here. Then around 1 million years ago here. So that is how the eruptions have created those kinds of islands earlier. So that gives you an idea that the plate is moving in this direction in general, right? So present day, the eruption is happening here. But the chain of evidences indicate that all of these islands which have been created, they have been created as a result of the same material exiting from the Hawaiian mantle plume and Hawaiian hotspot. So that tells you that at one point of time, even this area, that would have been present directly above that hotspot. And that means initially it would have moved slightly north, then it would have slightly started moving northwest. So that is how you get a chain of these kinds of islands. Okay. Why this shifts? Because of plate movement. Just like that, plates, they move. That is why they move. Every plate moves. So on top of the mantle plume also, or the hotspot also, that plate will also end up moving. So when the plate moves, it will leave behind a trail of these landforms. Okay, right. In which layer of the earth magma chamber is created? In the region at the boundary zone between lithosphere and asthenosphere. That is where magma chamber is created. If the plate is not moving, will it lead to the formation of composite volcanoes? Very easily. But you don't have a case across the planet, you don't have a situation where a particular plate has not moved for 200 million years or 300 million years. You will not come across any plate which has not undergone a motion like that. So the plates will invariably move. Okay. Now, then here we come across intrusive volcanic landforms. So while discussing the volcanic eruption, we have also discussed about the fact that in certain cases, the molten materials in the magma chamber, if you don't have the presence of enough amount of gases, the molten materials, they will start solidifying there itself. And when they start solidifying there itself, that is when they will form igneous rocks in the interior of the planet, in the region around lithosphere. And thereby, when many of the times it can happen, for example, let's say this is the region of the surface and you have the magma which tries to rise up, but then the surface is so hard, or maybe they don't have enough pressure. So let's assume they have solidified like this here itself, right? So this is where, when they solidify, what do they form? So this is solidified magma. So when they get solidified, that is when they form intrusive igneous rocks. Intrusive igneous rocks. Okay. Now, how is it that we get to know that, okay, here you have the intrusive igneous rocks which are created? So over a period of time, just like is the case across the entirety of the planet, over a period of time, this particular land surface will experience erosional activities. Wind, river, rainwater, everything will be acting in that region. And maybe over a period of 100 million years, 200 million years, maybe even 300 million years, that region or the top portion of it will be eroded away. And when that is eroded away, these intrusive rocks that are very hard, they will be exposed. And that is when we get to know that, okay, in this region, you might have had the existence of an intrusive igneous landform, or this landform that we see, this would have been created underneath. And now it stands exposed because the above layers are simply removed. Okay, so the lava that is discharged during volcanic eruptions on cooling develops into igneous rocks. The cooling may take place either after arriving on the surface or also while the magma is still in the crustal portion. According to the location of the cooling of lava, igneous rocks are categorized as intrusive or plutonic rocks, or extrusive and volcanic rocks. Now, depending upon the shape in which that solidification takes place, how it has solidified, where it has solidified. So, depending upon the shape in which the solidification occurs, it is further subdivided or subclassified into batholiths, laccoliths, lupoliths, faccoliths, sills, dikes, and so on. That is largely based upon how that solidification or where that solidification has taken place. In what shape has the solidification taken place? For example, In certain cases, the entire magma chamber in itself solidifies. And when the entirety of the magma chamber undergoes solidification, then you have a large area, a large dome-like structure. And when that is exposed, that is again an intrusive landform. So like that, you have various different types. So for example, here, if you take a look at the image, so basically, observe. In case this entire magma chamber that you observe, if that in itself solidifies, so that will create a very unique kind of intrusive landform. So that is what is referred to as a batholith. So a batholith is the cooled portion of the magma chamber. Okay, it is a large body of magmatic material that cools in the inner portion. The magma chamber in itself does not have enough pressure or energy to be able to expel all the molten materials outside. Now, they appear on the surface only after the denudation process, that is the erosional and the weathering process of the rocks, that eliminates the overlying materials. Then this is something which is exposed. Example, this is a batholith, right? So imagine at one point of time, you would have had this as an active magma chamber. And imagine at one point of time, there would have been overlying rock layers above it. But now that the overlying rock layers have been removed, have been eroded, this area is exposed. So that is what is the kind of a cooled down portion of the magma chamber in the interior. That is a batholith. So accordingly, based upon the shape in which the cooling has happened, you also have laccolith. So laccoliths are created, for example, when the magma tries to come above the magma chamber, it is coming up, it is hitting the crustal portion, it is creating a kind of a bulge, but it is unable to break through the crust. So in that case, this portion which has risen up and this portion which is pushing the crust, it solidifies there itself. So when the above portions they are eroded, so the rising dome-like feature that you see, that is a laccolith. In general, in the case of a laccolith, you will observe that the magma tries to rise up at one point of time. Magma chamber would be here. Magma chamber would be somewhere here. And that is where magma would have tried to rise, but it would not have managed to break through the surface. So over a period of time, that is when it creates this kind of a structure. When the above portions are eroded, this is what is a laccolith. Okay, so here the base is level. So laccoliths, if you have to draw the shape of it, so there you will have a kind of a connectivity from the lower magma chamber, ancient magma chamber, which would also have solidified, and it would give you a kind of a flattish base and a dome-like top, just like a kind of a mushroom of sorts. So that is where this is going to be the shape of the laccolith in general. Then lopolith. What is a lopolith? Lopolith is basically again a kind of a cooling process, but here the shape is the inverted portion of, or in the inverted form of, a laccolith. So for example, suppose here as you can see, it is a solid rock form with a roughly flat top and a shallow convex base, right? May have a feeder dike or pipe below connecting it to the main magma chamber. Connecting it to the old magma chamber. Okay. So for example, suppose this is the crust. And here in the crustal layer, let's suppose from the magma chamber, this is the older magma chamber, materials have tried to rise up through the various sections of the rocks. They have tried to rise up. But over a period of time, they lose temperature, right? Over a period of 100,000 of years, they lose temperature, they lose pressure in case they don't have gases. And then you have the solidification, which happens somewhere like this, right? So that is where you have a flat top. So this portion gets solidified. The entire portion gets solidified in the way, but this is solidified. Over a period of time, when this gets exposed, we refer to it as a lopolith. Okay. Now, then you have phacolith. So we have seen already that rocks, in many of the cases, they are compressed, they are elongated. So the rock layers also will experience a kind of a compression in many of the cases. Now, when the rock layers are compressed ever so slightly, that will lead to the generation of various different kinds of folds inside. So let's say the rock layer is basically having multiple layers, somewhat like this, because it is getting compressed from both sides. Let us say the rock layer is having a shape like this. Now here, the molten materials, they try to come out, but they end up solidifying within those layers, maybe somewhat like this or somewhat like this. So these are referred to as phacoliths. So when we say phacoliths, it is a wavy mass of intrusive rocks formed at the base of synclines or the top of anticlines. Synclines and anticlines we will study very quickly or very soon. So synclines, so whenever there is a kind of a fold, the fold will have a section like this. These are referred to as anticlines, and these are referred to as synclines. So this is something which has solidified along a syncline, and this has solidified along an anticline. So that is a phacolith. So these wavy materials have a definite outlet to source underneath in the form of the magma chamber, and that is how the molten materials would have solidified in the layers between the rocks. Now, you also have sills and sheets. So sometimes when the molten materials, they spread in the interior within the horizontal layers of the rocks, so that is what forms sills. And if that spread is very very thin, that is what leads to the creation of a sheet like feature as well. Okay, so that is what creates the existence or the formation of a sill or a sheet in general. So sills are basically near horizontal bodies of intrusive rocks, and if it is very thin, the thickness is less, then it is referred to as sheets in general. Okay, so for example, observe this feature here. Observe that there is a horizontal portion of materials. Now, at one point of time in the past, it would be nothing but the molten materials which have spread themselves between the layers of the rocks. So these are what is referred to as a sill. Okay, so that is how it spreads between the layers and it solidifies in that region itself. That is what we refer to as sills. Then we have dikes, dike formation. So dikes are basically wall-like formation. So where you have vertical rise, and in that vertical rise itself, you have the magma which solidifies in the interior. So wall-like formation of solid magma, oftentimes nearly vertical, that is what is referred to as a dike. So again, if I take you back to this particular image, suppose here, observe in this image, you'll find that the horizontal spread leads to the formation of sill. Then observe that a kind of a dome-like feature leads to the formation of a laccolith, right? Then here, if it has to solidify in these vertical sections itself, that is what is referred to as dikes. So oftentimes these dikes are nothing but vertical wall-like features that you come across. Okay, you have a lot of these dikes present in the region around South Africa. Some portions of Deccan Plateau in India also has got the presence of these dikes. Generally, because they experience so much of pressure, these are the areas which are rich in mineral deposits as well. Now, then we come up to the types of magma, that is the chemical composition of magma. So magma, we have already seen that it is made up of different materials, different elements, and different compounds. That is what constitutes the magma in general. So when we say magma, broadly it is classified based upon the chemical composition into mafic, right? And then felsic. So mafic. So Ma stands for basically magnesium and Fic represents iron. So mafic is going to be having very poor silica content, low silica content. And the felsic here, basically it will be low in iron and magnesium and very rich in silica. So the rocks which will be formed as a result of which, that is the mafic rocks, they will have, we have seen in the portion of igneous rock, there we have written it in that slide as well. So there you will observe that the mafic rocks, they will be darker in appearance, having a greater density as well. They will be heavier in general. Whereas the felsic ones, because they are so rich in silica, they will have lighter coloration pattern. They will be having lesser density as well. So hence they will be lighter in weight capacity also. And the viscosity, that is the ability of the magmatic material to flow, that viscosity is also something which is controlled by the presence of silica. In most of the cases, viscosity is controlled by the presence of silica, the availability or the abundance of silica which is present. So for example, mafic, when we say this is poor in silica, poor in silica, and that is why here, as you will observe, the flow is very easy. So low viscosity. Whereas when we say felsic, abundant in silica or rich in silica, and will be highly viscous. Highly viscous. And that is how even the rocks which are created, we have seen what their properties will be. So based upon the kind of magma which is there, there also we can get an idea about the explosivity of the eruption in general. For example, mafic magma flows easily. Will it have explosive eruptions? No. So here you will have non-explosive eruptions, which is better. Better is that no eruption takes place. Okay, so it is not the aspect of that which volcanic eruption is better. Please don't think about that. Ideally, no eruption should take place for us humans, but eruption is taking place. We have to analyze. So both of them have their own individual properties. So this is where non-explosive eruption. Non-explosive eruption. So here, generally you will find dome-like features created or shield volcanoes which get created. And in this case, you will observe explosive eruption. Explosive eruption which happens, and that generally will lead to the formation of features such as cinder cones. Cinder cones and lava domes. They get created as a consequence of it. Okay? Now, that is where this is a kind of a chart which gives you an idea that how silica content ends up determining whether it will be explosive, viscous or not. So when the silica content is less, we can easily say it will be mafic, right? So mafic means viscosity is low, means flow is easy. It can flow like water almost. So that is where non-explosive eruption. When the silica content is very high, that means it is felsic. That means the viscosity is high. That means it is unable to flow very easily. It is sticky in nature. Just like think about honey. Try to pour honey somewhere, how sticky it is. And then there you will need an explosive eruption to occur in that place. So that is how the type of magmatic material ends up determining the type of eruption which occurs as well. Now, this is the distribution of volcanoes across the globe. In almost all the cases, you will observe that volcanic eruption. So, if a question is asked with regards to discuss and describe the eruption, volcanic eruptions across the globe, you have to first of all write that volcanic eruptions occur in areas where you have the plate boundaries, in areas where you have hotspots created by mantle plumes. So, areas, which areas you will have? Plate boundaries and also in hotspots created or fueled by mantle, not mental, mantle. If you have plumes rising up at a mental level, that is more dangerous. So this is mantle plumes, right? So in these areas, you will observe the eruptions to be happening. And then you can slowly and steadily also keep on discussing about the fact that where in the or why it is in these areas that eruption is happening, because of oceanic convergence or oceanic continental convergence. In certain cases, for example, this La Palma that you see near Canary Islands, that is where a transform movement is leading to an eruption. Then all across the region of the Atlantic, if you will observe, the region around Atlantic, because of divergence, the eruption is happening. Then here, that is the Reunion Island. This is a hot spot. This is also a hot spot. In fact, this is also turning out to be a hot spot near the region of Iceland. It is suspected that there is a mantle plume which is active underneath, which is further leading to the expansion of the Atlantic. And it is predicted that because of that increased divergence, the North American plate will further separate from Eurasian plate, South American plate will further separate from African plate, even Greenland will be further moving away from Europe, and overall Pacific plate will be compressed from all sides, and it can over a period of time be reduced quite significantly. So that is basically the global distribution of volcanoes. It's absolutely okay to do typing mistakes, so please don't worry about it. So here now we come to folding and faulting. Now what do we mean by folding and faulting? So the rocks, when we talk about it, rocks in general, they experience forces acting from the interior, right? Now those forces acting from the interior, they can always end up influencing a particular type of a rock. So over a period of time, let's suppose this is the rock, it can get compressed, it can be elongated or stretched. You can have multiple different types of consequences happening in this case, right? So all these will lead to certain impacts. The rocks can get elongated, stretched, maybe when they are compressed, then what will happen? They will create a kind of a fold. So that is what is folding and faulting. This is a result of the forces acting from the interior. A result of forces acting from interior, right? And the forces acting from the interior of the planet, what do we refer to them as? They are the endogenic forces. Yes, Rishti, fault means cracks. We will analyze all the kinds of faults as well. Don't worry. This is what is endogenic. Okay. So that is what you have as folding and faulting, as we will take a look into. Now here, yeah. So here, if you will analyze, when we talk about folding, folding is a bend in the rock that is generally a response generated due to the compressional force. Due to the force of compression, that is why a folding results. Now, as a result or as a consequence of folding, you have the creation of this kind of a structure in the rock, something very similar to like this, right? So this is what is referred to as a fold. Okay, now this fold will have a kind of a central axis. Okay, so observe here, this will be the central axis of the fold, and these will be the limbs of the fold, of the fold. Okay, so here when the rocks they get folded, when the rocks they get compressed, that is when they get folded. That is when they generate a kind of a wave like structure. The wave like structure that you see. So this we have seen, this is the anticline and this is the syncline. So the definition of it is that anticline is the upthrown part of the fold and syncline is the downthrown part of the fold. So initially when the compression happens, I will take the help of this piece of paper. So if suppose this is the rock surface, now here, if let's say when we talk about the compression will be acting generally from both sides. Sometimes it can be more from one side, less from the other side. It can be symmetrical forces, asymmetrical forces which can act. So in the initial stages when the compression is happening, it will start folding, right? So the land in this region will suddenly be lifted upwards. It will fold and will continue. Now, over a period of time, let's assume that initially this fold is happening. You will observe that it is simply a kind of a symmetry which is observed here. But what if we, as is the case with the Indian plate and the Eurasian plate, now there also the rocks are getting compressed and are getting folded. Suppose this is the side of the Indian plate. So as this starts pushing, observe what is happening to the shape of the fold. It is getting irregular. If I continue this, what will further happen? This fold will further get more and more irregular. And that is what generally happens. And the folds, their shape keeps on changing with the passage of time, with the change in the amount and the magnitude of force as well. So initially, when the fold is happening, it will be very smooth, very symmetrical. But if I start increasing the pressure from one end, observe what is happening at the other end. It will continue eventually till the fold becomes almost horizontal. Now, what if the force keeps on getting applied even beyond than this? What will happen in that case? In that case, the rocks in this portion that you see, they will be compressed beyond their elastic limit. And that is when the rocks will crack, just like in the case of Himalayas. and they will start sliding over each other. That will be creation of a kind of a fault in general. So there you will see that the younger folds, they appear like this, whereas the older folds, they have no symmetry, and eventually they can develop a kind of a crack as well. So folds are classified into various types depending upon the shape that they assume, depending upon the shape that they exhibit. Okay, so for example, if it is symmetrical from both ends, it is a symmetrical fold. Take the case of the symmetrical fold. Here you have equal compressional forces acting from both ends. So equal compressional forces acting from both ends. Right? So in that case, what do you observe? You observe the formation of a symmetrical fold. But then as that continues, if let's say that kind of a force which is applied, if it continues, what will happen? It will get asymmetrical. Both sides will not exhibit the same angle. So over a period of time, there's a variation in the compressional stress from any of the side. It creates a kind of an asymmetrical fold in general. In the region of Himalayas, especially in the region of Himalayas, particularly in this region of Shivalik, you will find certain cases of symmetrical fold. In the cases of greater Himalayas, you will find many cases of asymmetrical fold. That is why when we come to Indian geography, we will study that in the region of Great Himalayas, or the oldest one, the shape is somewhat like this. And that is why the Himalayas also are particularly known as a topography which is referred to as hogback topography, that we will study when we come to the portion of Indian geography. So this is how the asymmetrical fold is created. Then you have the recumbent fold. So recumbent fold is created when you have this folding or the compression of rocks which continue to happen, and thereby it becomes almost horizontal. That is a recumbent fold. That is where in the larger rock layers, let's suppose this is the mountain that you observe, but we don't observe the rocks underneath. Maybe the rocks, they get folded to an extent like this. So this is a kind of a recumbent fold. It is also referred to as a sleeping fold or a horizontal fold because of the shape that it takes. Now, in this case, if suppose this is your recumbent fold. Now, if the force keeps on getting applied, just like in the case of Himalayas, there also, now as the force from the Indian plate keeps on getting applied, you have certain areas where the rocks have taken this shape. So as the force keeps on getting applied, what will happen? It will simply break. It will break from here, and this portion will travel further. It will start sliding over the other. And that is what is referred to as a broken fold or nappy. So, in such folds, induced compressional stress surpasses the ductile characteristic of the rock. Ductility is what? Ductility is ability to be stretched. So, that ability is surpassed, and that is when it simply breaks away. So, for example, if you will observe here, so observe, while this is an asymmetrical fold here, asymmetrical fold here. Here you will observe the presence of broken fold. Broken fold. Yes, this is a real picture. All the images indicated here are real picture. Okay. Yes, in sleeping fold also the rocks will break. Now, this is the various different kinds of folds which are experienced. It can sometimes be experienced in the same plate due to compression, or in between the margin of the plates when continent collides. There also you can experience this. But then sometimes when there is a greater amount of stress which is induced. So rock layers do not always respond to stress by folding. Rocks near the surface, they are generally cooler. Anything which is cold, it breaks easily, doesn't it? You would have seen that if you put a metal container into the freezer, maybe a can of soft drink, if you put it in the freezer for a long time, when it becomes very cold, you can virtually break it or cut it through, because the colder things break easily. So the rocky layers or the rocks on the surface, they are much colder than the rocks underneath. So upon application of forces, the surface layer can break very easily. And when it breaks, it develops cracks, which we refer to as faults. So they tend to be more brittle, that is, they break very easily. So a sudden stress on these rocks may reach a rupture point, resulting in cracking and breaking of the rock structure. Now, here, if you analyze, if there is a breaking of rock without any relative displacement on either side, the crack in that case is called a joint. If there is a relative movement between the rocks, that is, let's say these two are moving with respect to each other, any kind of motion which is happening, if there is such a development of a crack that the rocks, they start to move with respect to each other, then the crack is known as a fault. Okay, and when faulting occurs, oftentimes across the fault planes, the rocks, they start sliding. So when faulting occurs, the rocks on one side move relative to the rocks on the other side along the surface of the fault, which is referred to as the fault plane. So that is what we have as the fault. Now, faults, just like the case of the faults, faults are also classified into various types and various paths. So you have normal fault, reverse fault, a mixture of two normal faults, a mixture of two reverse faults. So you have different types of faults which are in existence. So when we talk about the types of faults, for example, suppose we take the case of normal fault. So normal fault is created due to tensional stress. That is the tensional force when the rocks are getting pulled apart. So here, many of the times what happens is, suppose this is a kind of a rock. Okay. Now let's suppose there is a tension. Just like take this pen. If I'm pulling it from both ends, here, if it is not stretchable enough, and it will vary with different materials, if it is not stretchable enough, that is when it will start to develop some crack if I continue to pull it. So let's say it has developed a kind of a crack here, right? Further tension will further pull the crack. The crack continues to emerge. Now, after this, if there is tension, now, then there will be, here you will observe that a joint has been created now, till now. Now, further, if there is more tension, then there will be movement across this joint. And that is what creates a fault. When there is movement across a joint, a fault is created. So, thereby, now when the movement starts, in what direction will the movement happen? One portion will simply slide, isn't it? So you will have the creation of a condition somewhat like this. One portion simply slides down. So that is where on one side you will have a steep wall-like feature almost, which are also referred to as fault scarp. So this is what is your fault plane in general. Right? Now here, this is what creates a kind of a landform. Many of the times you would have come across a situation where the land appears to be flat for a long time or for a large area, and suddenly you have the presence of a lot of hilly areas or the upland portion. So that is what is created as a result of this, and this is a normal fault. Then after that, the compressional forces, they also create a kind of a fault, and that is what we refer to as the reverse fault. So here, when you have the compressional forces which are acting in the case of the rock, suppose this is the rock, suppose this is the rock part, and you have compressional forces which are acting. Now these compressional forces, if they can lead to folding as well in certain cases. But what if the material is so hard it does not get folded easily? Suppose if you apply compressional forces across this kind of a material, it will easily get folded. But what if I apply compressional force across this kind of a material, that is the pen in my hand? Will it get folded? No. So if I apply more compressional force, what will happen? It will develop a kind of a crack, isn't it? It will develop a kind of a crack. This crack, unless and until there is no movement happening across this crack, what is it referred to as? A joint. So in the crack, if there is no movement happening across both sides, it is a joint till that point of time. But if furthermore I keep on applying this force, then what will happen? One side will simply be forced to climb over the other, and you will have a condition somewhat like this. Now that there is a relative motion along this crack, so now it will be referred to as a fault. Observe, observe the image carefully and observe this thin line that I am tracing. This is the example of a reverse fault. At one point of time, based upon the rocks and the layers of the rocks, you can imagine that this layer that you see, doesn't it have a kind of a similarity with this layer? So imagine at one point of time, this layer would have been present somewhere here, but it has climbed up. Why? Because of that compressional force. So this is where you have the rocks which move in a direction which is opposite to the general direction of the gravitational pull. That is, they are thrown upwards, and hence the name reverse fault. Okay? Now, then we have graben. Graben is a resultant of two normal faults which are created. So, a result of two normal faults. Result of two normal faults. Okay. So suppose if I consider a large rocky structure, here, large area, there is tension, let's suppose, from both ends. So over a period of time, what will happen? This will start developing certain cracks, isn't it? Now, it is not necessary that the cracks will be developed only across one area. You might have the simultaneous weakening of the rock and development of another crack. So, over a period of time, both of these cracks will intensify. They will grow across these rocks, right? They will end up becoming joints. Now, if there is further tensional pull, what will happen to the central portion? There is nothing holding the central portion in its place. So it will slowly and steadily start to sink. And that is where you will have a kind of a landform, which will be very similar to something like this. This is what we refer to as a rift valley. Okay, this is what we refer to as a kind of a rift valley, as you can see, or a graben, where the central portion has sunk down. Okay, now in general the graben doesn't appear like this. It doesn't give you the appearance of as uniform a picture as you see. In general, what you will observe, that over a period of time the winds are moving, so the winds will erode these areas, and these areas will be eroded in a certain manner. So it will give you an appearance as if there are a lot of hills surrounding this, but eventually it is a kind of nothing but an upraised portion. I'll show you how it looks like. In a couple of slides, I will show you what the real appearance does look like. Then we have a combination of two reverse faults. And two reverse faults means compressional forces. So when I have compressional forces acting from both ends, cracks can happen. And thereby, if this continues to happen, let's say a crack has developed across this plane, a joint has developed. And furthermore, if I continue to push, what will be the resultant? The central portion will be thrown upwards. So that creates a kind of a landform which has been pushed up, vertically up, because of compression of both sides. The central portion has been pushed up. That is what is referred to as a horst or a horst fault. So it results when the development of two reverse faults causes the block of rock to be simply pushed up. This is over a period of time. This will also not appear like this. This will also experience erosion by the wind, and it will also be reduced to certain mountain or hill-like feature. This leads to the creation of what we refer to as block mountains. Block mountains. Example of block mountains: you have Vindhyas in India. Then Vosges in Europe. Okay, these are the examples. So this is what it appears to look like. So these are the areas of graben, right? The depressed portions that you see, these are the areas of graben, and these are the upraised portion in general, the horst. So that is where generally near the region of a horst or a block mountain, you will come across in general a graben as well. So for example, if you take the Indian case, so this represents very ideally the Indian case, where on one side you have the Vindhyas, on one side, look at the map after the session, you will get an idea. You have the Satpuras, and in between you have a rift valley through which a major river passes through. And what is that river? A major river passes through, and that is where we have the very good industry. It is Narmada Rift Valley. Okay, that is how you have the existence of these in real life scenario. Okay, The force we are discussing in folding is convergence of plates, not necessarily the plate boundaries in itself, Yashika. Sometimes it also happens that, for example, in the same plate, there are compressional forces acting from the inside. So in the same plate, also in a small region, there is compression. So not necessarily at the plate boundaries themselves. Okay. Facolates are not folded. No. This is how the materials they solidify. So that is where we'll end the session for today, and tomorrow we'll initiate the discussion for landforms, erosional and depositional. Saturday we are going to have an extra session from 7 to 11. So tomorrow we will be ending the portion of geomorphology. We will be discussing the previous year questions associated with geomorphology, and we will try to enter the area of climatology as well tomorrow. Okay. So I hope today's session has been fruitful for you guys, in the sense that you have extracted something. If not something, at least you have extracted the fact that recorded videos will be available to you. So that is where we'll end it. And difference between sills and dikes, Salam, sills basically are horizontal solidification of magma, and dikes are vertical solidification. Okay. Earth plate create same as mantle plume or hotspot create? No, Sarthak. So you have had multiple different volcanic eruptions initially happening all across the region of the crust that has created the crustal portion. What forces cause such compression? It is the internal or the endogenic forces. I will give you the classification of these forces as well. Tomorrow is a class, yes. Amit, what summarization do you need, my dear friend? Horst Subarna is a combination of two reverse faults where the central portion is uplifted. Graben is a combination of two normal faults where the central portion subsides. Devansh, no. The uplift of the Tethys Sea was not entirely that of a Horst, even though some portion of the Tethyan region was simply pushed up because of the internal forces that were present. But nonetheless, there was a folding which happened in the Tethyan sea floor as well. Before volcanoes, Amit, we had discussed about the earthquakes, the global distribution of earthquakes, where in India the earthquakes occur. And we had discussed the aspect of anthropogenically induced earthquakes or induced seismicity. That is by dams, by hydrocarbon extraction. That is something we had discussed. Pranay, majority of plate movement is due to asthenosphere? Yes. Kivika, silica is SiO2. SiO2, that is silica. The sand that you see, that is made up of silica. Why magma chamber becomes empty when the mantle? So not in every magma chamber will you have the condition present where the mantle plume is filling it. Mantle plumes are present only in certain areas. Magma chamber is present underneath every volcanic eruption. So in the areas where the mantle plume is there, magma chamber will be always full. But in areas where there is no mantle plume, eventually the magma chamber will empty out. Uh, yes, Devansh, due to lack of gases, sometimes naturally the temperature starts getting dissipated in the surrounding areas. That also brings about a cooling effect. Okay. Block mountains are created where suddenly a portion is pushed up. Fold mountains are created when the region is compressed and folded. What happens when there is compression of faults host? So hosts themselves are created due to compression, right? So that is where the compression leads to development of cracks in the central portion being pushed up. That is why they are created. Can reason for induced earthquake for dam that is surface deform in ocean? No. See, the oceanic crust is denser, right? So that is where Gagan, it can withstand that pressure overall. Yes, Pranay, you can obviously write that. Sarthak, no, they won't affect the movement of plates. Harshita, the movement of plates can create the force and faults or the force generated, both of them. Many of the times in the case of transform movement, that rough motion of the plates that generates cracks, that is also a fault. So initially when the cracks are developed, it is referred to as a joint, but when there's motion which starts happening across the cracks, you have a fault which develops. So within the same plate as well, because when you take a look at Indian plate, you have many fault lines in Indian plate. The Himalayan frontal fault, then you have the Vindhyan Scarpa, the fault, then you have the Western fault. You have many faults, and it can exist in between the plates as well. Okay. Yaram Seti, in Earth, like in remaining planets, also occur earthquakes? No. That is because when we talk about the regions in general for the terrestrial planets, gaseous planets, obviously, gaseous giants, no question of having the shaking of the ground surface, no hard ground is there. In the case of the other terrestrial planets, you don't have the same residual heat which is trapped, and in most of them, the residual heat has been released. So, what is left behind is a condensed solid in general, right? So, that is why, and all the plate movement is basically driven from the residual heat present in the interior since the time of formation of the planet. Yes, you have your webinar as well. Fair enough. Last question, I'll take a couple of questions. Um, that is, Satpura is an example. It is also an example of a kind of a host. Abhinav, can East African Rift Valley form because Somalian plate moves away from the Indian plate? It is forming because there is a convection current which has emerged underneath the underneath the African plate, and it is said that this generation or this convection current has come into existence somewhere around a couple of million years back. That is why Mount Kilimanjaro had so many eruptions. In fact, in the region around Kilimanjaro, the last major eruption was around 2 lakh years ago. But still, the entire region is rifting away. Okay? No, that is something I will leave for you guys to do. Anyways, the examples for the block mountain Subhana that we are giving, that is more than sufficient. For optional, you need to study fold and block mountains in detail. For general studies, you just need to know what they are and a couple of examples. Ayushman, I hope the session was helpful for you. I hope something is understood, even though you would have missed the earlier classes. Can asthenosphere create a volcano, Ranjan? Obviously, yes, because that can also generate a lot of convection current. SK, yes, that can lead to earthquake generation in certain cases. Prithvi, mostly, wherever you have the graben, a side host is observed in that case. Devansh, true. Geophysical characteristics of the circum-Pacific zone along with the trenches as well. Don't forget the trenches. Okay. So that is where I'll end the session for the day. We meet again tomorrow, and then we will continue further. Lectures are sufficient for the mains examination? Yes. Just enrich your content with the help of current affairs, more than sufficient. So that is where we'll end the session till we meet again tomorrow. Take care of yourself. Goodbye. Thank you.